Section 1.9 Matrix of a linear transformation. So we start with the theorem. Theorem 10 it says that let T be a transformation from Rn to Rm and let it be a linear transformation. Then there exists a unique matrix A such that T of x is equal to Ax. So a transformation is completely described by by this matrix A, and this is called standard matrix for the linear transformation. Now there are some special vectors in each space. So in R2, the smallest space that we know, so we have a linear vector 1 0. So note that this will be we call it the unit vector along the horizontal axis. So this time we are going to call the axis x1 x2, not xy, so x2. So the 1 0 vector over here is the vector on the horizontal axis of size 1, and then 0 1 is the unit vector along the vertical axis, and we have special names for them. So the one on the horizontal is called E1, is denoted by E1 bar, and then the one on the vertical axis is called denoted by E2 bar. Now in R3 we will have 3 vectors, and R4 we will have 4 vectors, and so on. So in R3 E1 is going to be 1 0 0. So note here the way you can figure out what E1, E2, E3 are depending on what axes we are talking about. So it will have only one component of the vector will be 1, and the rest of the components will be 0. So when we talk about, so this will R3 x1 x2 x3. So along here, along this axis, the unit vector E1 will be 1 0 0. Along the x2 axis we will have the E2 vector, which will be 0 1 0, and along the x3 axis we will have the E3 vector, which is 0 0 1. And you should be able to see that in R4, for example, E1 will be 1 0 0 0, so there will be another 0, and then second will be 0 1 0 0, then third will be 0 0 1 0, and the fourth will be 0 0 0 1, and so on. So this is how you can have these vectors along the axes. Okay, so now any vector in the space can be written as a combination of these two vectors. So these are, for example, in R2, E1 and E2 are linearly independent vectors, and they span the R2. So any vector x can be written as x1 E1 plus x2 E2. In the same way, any vector in R3 can be written as x1 E1 plus x2 E2 plus x3 E3, and so on. So now if I have T of x, then T of x will be x1 T of E1, because we can pull out the x1, which is a constant. So we know that the linearity property of the T lets us do that. So we can write it like this. So now you see these vectors that we are getting here, these are form the columns of the A matrix. So the A matrix will be T of E1, T of E2, T of E3. So if A is not given but the transformation is given, we can figure out what the matrix will be. So here is an example. Find the standard matrix for T going from R3 to R2 such that T of E1 is giving you 1 3, T of E2 is giving you 4 negative 1, T of E3 is minus 5 4. So you see these are your column vectors, right? So the first one is 1 3, second is 4 minus 1, so second column of A, and then negative 5 for third column of A. So this is your standard matrix. Okay, let's look at some special transformation matrix of transformation. So when you have a matrix like this, it actually gives us a shear. Yeah, it doesn't give us a dilation, it gives us a shear. Rotation about origin by angle theta is this matrix. Cosine of theta, sine of theta, minus sine of theta, cosine of theta. So first row is cosine theta minus sine theta, second row is sine theta cosine theta. What I have done here is I take like an arbitrary general vector, because it has to be of 2 by 1 order vector, because of the matrix is 2 by 2. So we are looking at the matrices, special matrices in R2. So when I multiply it by this is what I am getting, and this is like what happens when we have a shear. So this matrix, if you multiply corners of a shape by this matrix, if you multiply each corner, it will rotate the shape by angle theta in the anti-clockwise direction. So this matrix is, when you multiply the vector with it, what it does, it reflects the vector through x1 axis. So here is the picture. So this was the black is the original vector x1 x2, and when I multiplied with the this matrix, I got x1 minus x2. So I have the reflection of the vector along the or over the x1 axis. Then this one, it reflects the vector about the x2 axis. So you can see this is x2, this is x1. Now what does this do? It switches the x1 and x2. This matrix switches x1 and x2. So it makes the x2 take the position of x1 and x1 takes the value of x2. So this matrix, or you can also say here, what this matrix did, it reflected the vector about the line y is equal to x. Okay, the next one, the 0, minus 1, negative 1, 0, this reflects the, so this is what it does. So it reflects this through the line x is equal to minus x1, which means about this line. So it reflects it about this line. The next one, so this one, so this reflects it about the origin. So see the difference between these two, number 6 and number 7, slight difference, and then they perform two different acts. Now if you have a matrix like this one, now look at this one and the first one, compare these two. So in the first one we had 3 non-zero entries, whereas in the 8th we have only 2 non-zero entries. So this matrix, when you multiply a vector by it, it dilates, or it kind of dilates mean it kind of stretches or it compresses, or sometimes we say expands or contracts the shape. And if the k is moved to another place, so if the k is moved over here, first it was in the first place and now it is in the second. First it was in number 8, it was first column and first row. In 9 the k is in the second row and second column, so now it expands and contracts vertically. So here is a shape of it. It is 9, 10. So notice here 3 non-zero entries. It is similar to what we had in 1. So we had a shear by a factor of k, and now we have a horizontal shear by a factor of k. So over there we had a shear by a factor of k. Actually that was a, I think this is wrong. This is a horizontal shear and this is a vertical shear. Projection onto the x-axis. So if you have a matrix like this 1 0 0, so what it gives you is the projection of the shape on the x1 axis, and if we put the 1 in this position, it gives the projection on the x2 axis. Okay, I will do some examples and some more theorems in the next video.